Okay, as we continue our discussion of the channel capacity theorem, we're going to move on to this next section where we look at bandwidth, how bandwidth plays into this. And bandwidth tells us how fast we can send pulses through a channel. And once we have that, we can move on to sort of a plausibility argument about the channel capacity theorem. Okay, so first of all, let's attack this bandwidth question. All right, so we're going to start with pulses that we're familiar with. This is really a raised cosine pulse with a special case. It's a sinc function. Okay, so if you put beta equals 0 on a raised cosine pulse, you get the sinc function. And so we know what that looks like and why we used it. We used it because it was more efficient from a bandwidth point of view. In fact, it was our most efficient pulse shape that we could use for bandwidth. Okay, so a sinc function, of course, looks like this. And what we found was that we had 0 crossings at TS, minus TS, 2TS, and so forth and so on, because this pulse shape didn't have intersymbol interference, right? And then the amplitude that we use here, this would be one of our signal levels, all right? So in our 4-PAM system, this amplitude takes on values of 1, 3, minus 1, minus 3, so forth. Okay, if you went to 8 levels, you'd have 8 different amplitudes for this sinc pulse. All right, so then the question becomes, how fast can you send these through a channel? And what we know is that if you get distortion because of lack of bandwidth, it creates intersymbol interference and impairs our ability to communicate. So what we're going to do next is, this is the time domain sinc pulse, we'll call it PFT, and we'll look at its Fourier transform. Okay, so the Fourier transform is this rectangle function, but we're more used to seeing this as rectangle of f divided by the argument instead of multiplying by it. So you could put this as 1 over TS. Okay, close bracket. All right, so I know that this has this pulse, this rectangular pulse, looks like a rectangle, and it has an overall width of 1 over TS. Okay, so this upper edge right here would be 1 over 2 TS, and this lower edge would be minus 1 over 2 TS. All right, so we can relate that back to the bandwidth. All right, so what we know here is that the bandwidth is this width of positive frequencies, and so in our discussion we're letting B equal bandwidth, so the bandwidth is 1 over 2 TS. Okay, so let's get this back into a symbol rate or a message rate. How fast are we sending messages? How fast are we sending symbols? They mean the same thing. So 1 over TS is the message rate. How fast we're sending symbols through the channel. Each of those symbols carries different amplitude levels. Okay, so if I solve for 1 over 2 TS, I get 2B. Okay, so if I have a bandwidth of B hertz, that gives me a fix on how fast I can send levels or symbols through the channel. Okay, so once we use that result, we can put everything together. We can use some ideas on Huffman coding to talk about an efficient representation of the source. Put it all together and we can have a justification for the channel capacity theorem. So that's where we're going to go to next. Okay, so now we're ready to put this all together to sort of justify or explain or plausibility check, however you want to call it. It's not a proof. We'll talk about where things go a little bit wrong for this to be a proof. But it gives you some insight on why the channel capacity theorem would work. All right, so to make it clear, what we're talking about here is we have symbols that are being sent with a waveform. Okay, so we'll call that S of t. And we go through a channel. And in the channel is additive Gaussian noise, Gaussian white noise. So if the channel is different than that, if it was multiplicative noise, this wouldn't directly apply. Okay, but in general, we don't see channels like that in general. An additive white Gaussian noise model for a channel is reasonable. Okay, so what we would see then is we'd look at an output and we'd go through all of our processes that we do for communication systems. We have to sample the output at the right time and come up with, the received signal samples. Okay, and so the idea here is because we are sending a signal, there could be a certain noise power P, all right, and then we know we're sending signal plus noise, and so when we take a look at what we see on the output, the average power of the noise is going to be, the signal plus the noise is going to be S plus P. So that's the average power of the output. The output is signal plus noise. All right, so if you compare that, you would get, you're comparing it to the noise. The average power of the noise is simply P. Okay, so if we were going to do a full proof of this, we need to talk about codes that help us achieve zero probability of error, but we're not going to do it that way. We're just going to look at a plausibility argument on what would it take for there to be a reasonable chance of getting something through error-free in a communication system that's corrupted with noise. Okay, so if this is our output power, from circuit theory that you could come up with an average RMS voltage if you knew the average power of a voltage signal. Okay, so think of it this way: the RMS amplitude in this case would be square root of S plus P, and the RMS noise power, or noise amplitude you could think of, would be square root P. Okay, so if this is the RMS amplitude, okay, don't you think, or would it make sense that if we think about this, we know we're going to have certain levels, and so we could come up with sort of an average RMS separation of the levels. And because this was a power calculation, we're going to be taking plus and minus versions of the amplitudes. Okay, so if you had something set up and you said, okay, this is going to fall over a range, it's going to be square root of S plus P to minus square root of S plus P, you could divide that up into intervals, and you could get an idea of sort of the spacing of symbol levels, or levels in this case. Okay, so one idea of this would be that the separation between two amplitude levels would be roughly D. Okay, and if you think about this deeply, what we're talking about is on average, not the exact value that we would use under a power constraint. Okay, so it is a little bit of a hand-waving argument. Okay, but if you give me that, then you could say, well, if I take this amplitude, I know it goes plus and minus, so I need 2 S plus P, right? And if I have a number of levels, I could calculate D, and if you think about that, D should be divided by number of levels minus 1. Okay, so that's getting us close. It turns out you get the channel capacity result if you use D equals 2 square root S plus P divided by N instead of divided by N minus 1. Okay, so that's just a small deviation from the logic if we use divide by N instead of divide by N minus 1. Okay, so now let's think about that. If you're trying to distinguish between levels, wouldn't it make sense that the noise power on average has a constraint on D minus, or D over 2? All right, so I'm going to blow this up a little bit. Here's 2 symbol levels, all right, and what you would think of here, here's the range D. Okay, if I had an observation that was here, I would say, all right, that's going to go to, here's symbol level 1, here's symbol level 2. This is the decision point. If I had an observation in here, I would quantize that up to this level. If I had an observation in here, I would quantize that to this level. So you see, if the noise power takes you on average greater than d over 2, then on average you're going to get a lot of things that are outside of, if the noise is too spread out, it's going to take you into the wrong symbol levels. All right, so that's the argument, that d over 2 has to be at least square root of p. If you don't separate by the RMS value of the noise, you're just going to have a really hard time communicating. In fact, Shannon's result, eventually when you prove it right, shows that you cannot do error-free communications under those conditions. Okay, so we need d over 2 to be greater than square root of p. Well, we know what d is, all right? So we're going to take that and plug it in here, all right? And so we now have, I'm sorry, I pointed to the wrong thing. We're going to take this and plug this into here, okay? And so what we have then is that there's this inequality, all right? So I put d over 2, the 2's cancel, I get square root s plus p over square root of s plus p, the 2's cancel, has to be greater than, divided by n, carrying that along, has to be greater than square root p. All right, solving for that, all right, that tells me that n has to be less than, okay, I'm flipping this over, n has to be less than square root of s plus p over square root of p. All right, so it restricts the number of levels that we can have, and that makes intuitive sense, right? As I have a power constraint, what we talked about was under a power constraint, the levels have to be stacked closer and closer together. All right, if you have a certain amount of noise and a power constraint, eventually the noise will exceed the halfway point of the distance between the symbols, and when that happens, it's bad news for communicating. All right, we won't be able to communicate error-free. All right, so we now have a bound on the number of levels, okay? And we can also know that we have a certain number of symbols that we can send through the channel based on, the prior discussion about bandwidth. Okay, so here we go. What we know is that we have n levels. All right, n levels implies log 2 of n bits. Okay, so I'm going to do n levels per channel use or per message. Okay, that would be n log 2 bits per channel use. Okay, so let's take that. Okay, our channel capacity C is going to be log 2n bits per channel use, and then we know that we have 2b. Okay, when I say channel uses, I could also replace that with symbols that we send. Okay, and so we have 2b symbols per second. Okay, so I now have this as log 2 of n times 2b. All right, but we know what n is at this point, so we substitute n back into this equation. Okay, and our channel capacity is going to be 2b log base 2 of square root s plus p over square root p. Okay, then using property of logs, I can push this back into this argument here, and I would get b log base 2, square root of p over square root of p would be 1, plus square root of s, I'm sorry, if I push the 2 in, there'd be a square coming onto this term. Okay, if I push the 2 inside, okay, so I'm going to erase that so this line will be correct. Okay, if I do that, this would be 1 over s over p. Okay, so that's it. That's the channel capacity theorem. That's the result for the channel capacity theorem. And I've already told you that sometimes you'll see this as b log 2 of 1 plus s over 8 of b, okay? Because p is a function of bandwidth, and if it's additive white Gaussian noise, p as a function of bandwidth would turn out to be eta times b, where eta is just this constant you can use to adjust for the actual noise level. Okay, so there we have it. That's the channel capacity result. This is in bits per second. The actual proof is not constructive. Basically, it's done by looking at what happens on average with various codes, and you can prove that it is possible to communicate at a rate r up to c. As long as r is less than c, then you'll be able to do perfect communications through the channel, or it's an upper bound on communications. Okay, so I know there's a lot to that. You might have to think about these things a few times to sort this out in your mind, but it's an amazing and really cool result that helped push forward the frontier of communication theory.